Imagine you have a triangle inside a rectangular box. How much of the box do you think the triangle takes up? 2/3 maybe? Or does it depend on the triangle? Perhaps moving the tip around to different spots could change the proportions. This is a great math problem. It's fun, it's simple, and for me, it represents one of the many missed opportunities in the way math is usually taught in school. Let me show you why. First, a solution. Watch what happens when you cut the rectangle into two pieces, like this. It makes two rectangles, each cut diagonally in half by the sides of the triangle. So the triangle must take up exactly half of the box. This is what mathematics looks like at its best. It's an elegant question with a beautiful explanation. At first, the relationship between the triangle and the rectangle was a mystery, but it became immediately obvious just by drawing in that one little line, a line that I would bet a lot of young math students right now would think to draw under the right circumstances. But in many math classrooms, at least in the United States, which is what I'm the most familiar with, instead of being given the chance to find such a delightful solution on their own, those same students are oftentimes given something like this. Triangle area formula. A equals 1/2 b times h. The area of a triangle is equal to 1/2 its base times its height. This is the same conceptual material as the triangle in a box question. The box has area b times h, the triangle has area 1/2 b times h, so the triangle takes up half of the box. But presented in this way, there is no box, and there is no question, only an answer. Students aren't asked, how much of this box do you think this triangle takes up? They're told, this is how you find the area of a triangle. So what was a perfect opportunity to develop intuition and critical thinking skills on a bite-sized example has been completely skipped. The student is simply given an equation without ever having seen or appreciated the playful, imaginative environment where it comes from and why it's true. It's not just this one example. More often than not, our school system completely forgoes what is, in my opinion, the most crucial ingredient to mathematical development: asking questions. And not the kinds of questions that the student has already been fed the answers to via a set of rules and formulas. Questions that encourage the student to use their creativity, to see patterns, and to explore different ideas. To me, it's such a shame when I hear people say things like, "I'm not a math person," because I always wonder to myself, has this person really even experienced math from this more artistic perspective? Sure, there are plenty of people who enjoy thinking about numbers and doing calculations in their head. In fact, I was actually one of those people, especially as a kid. But if it hadn't been for some fantastic teachers of mine in high school that showed me there's so much more to mathematics than crunching numbers, and there's real beauty to be found outside of the standard way the subject is taught in school, I probably wouldn't have ended up studying theoretical computer science in college, or be doing what I am right now. I borrowed this triangle in a box question from an essay by Paul Lockhart called A Mathematician's Lament, where he talks about some problems he sees with K-12 math education. I really think this example does a great job at showcasing just how intuitive and approachable math can really be when taught in a way that unlocks the imaginative side of a student's brain, and how these opportunities are all too often missed in favor of alternatives that may get to the answer faster, but are probably a lot less inspiring to most people, and fail to develop some pretty important mathematical skills. I learned about A Mathematician's Lament from a couple of those great high school teachers I mentioned, and I'm super grateful that they made an effort to share it with me and my fellow classmates, because many of the points that Paul Lockhart makes in this essay really resonate with me. Here's another example that Lockhart gives. Take a semicircle and draw a triangle like this. Amazingly, no matter where you place the tip of the triangle along the semicircle, the angle at the tip will always be a right angle. If you ponder this setup for a bit, it's not immediately obvious why this should be true. It even feels unlikely. Like, surely the angle would change if you move the point around a bit, right? And here's where there's a perfect opportunity to stop and let the students ponder this question for themselves. What a beautiful moment to let them be mystified and wonder why this is true. Let them try drawing in all sorts of different lines and angles, and play around with different ideas. This is what math is all about. But in many classrooms, this might not ever happen. Instead, the beautiful question, the source of wonder and mystery, is often immediately answered with a list of densely notated statements and justifications for them. As Lockhart says, mathematics is not about erecting barriers between ourselves and our intuition and making simple things complicated. Mathematics is about removing obstacles to our intuition and keeping simple things simple. He then compares what he calls this unappetizing mess of a proof with one devised by one of his 7th graders. Take the triangle and rotate it around so it makes a 4-sided box inside the circle. Since the triangle got turned completely around, the sides of the box must be parallel, so it makes a parallelogram. But it can't be a slanted box because both of its diagonals are diameters of the circle, so they're equal, which means it must be an actual rectangle. That's why the corner is always a right angle. I hope you'll agree with me that this way of thinking about math is just so much more appealing. It's artistic, it's genuine, it's human. You can see and understand the flow of ideas. And none of this is to say that formalization and abstraction doesn't have its place. It absolutely does. But to quote Lockhart again, that place is not in a student's first introduction to mathematical argument. At least let people get familiar with some mathematical objects and learn what to expect from them before you start formalizing everything. I've been reminded of the standardized math curriculum's obsession with special notation and symbolic manipulation through recent experiences working with some high school students as a private tutor. One example that caught my attention in particular was the following exercise. Simplify. When I saw this, I immediately objected to the prompt. Like, what does simplify mean? There are many contexts in which the quote-unquote simplest form of an expression could be completely different from each other. After looking at the answer key, I eventually determined that simplify essentially meant to rewrite the fraction in such a way that there are no radicals in the denominator, and also you extract out from any radicals as big of a factor as you can. By the way, when you do that on this example, the final answer you get is this. And ironically, I think the original form is actually way simpler to think about for most purposes. Let me know in the comments what you think. Anyway, my point isn't that you shouldn't learn how to manipulate mathematical expressions into different forms. This is of course a useful skill. It's that the end goal of this exercise wasn't even connected to any problem that we were trying to solve. The student is simply taught that when you see something like this, you do this. And sure, sometimes you might want to think about a particular expression in its form where there are no radicals in the denominator. That could be a genuinely useful transformation in some cases. But I can think of several examples where it would actively make things more confusing to do so. In my last video, there was a time when the number square root of 1/2 came up. If I had quote-unquote simplified this expression, it would have turned into square root of 2 over 2. But the next step was to square that number. Obviously, when you square square root of 1/2, it's just 1/2. I would much rather think about it that way than squaring square root of 2 over 2. Now, I've been lucky enough to have the experience a few summers ago of being a long-term substitute math teacher at a high school. There's an anecdote from my Algebra 2 class that I find really encouraging, and I'd like to share it with you. You see, the students had been learning about systems of linear equations, and at the end of the year, I created a final project for them that introduced the concept of using matrices and some elementary operations on them to solve these kinds of problems. In the assignment, I asked a series of questions that guided them to try out these techniques, become confused, fail, and eventually succeed until they slowly got more comfortable with the material. And by the end, I asked them to use what they had learned to come up with a general procedure in a bullet point or numbered list to solve a system of linear equations with 3 variables, and test out their own procedure on a new example they came up with to see that it works. It was a hard question, and my students struggled a lot. But they had so much fun doing it. They had so many good questions and learned so much. Most importantly, the work was their own. They were way more excited to do this project than anything from the standard curriculum that year. And by the end, many of my students had essentially reinvented what's called the Gaussian elimination algorithm without even knowing it. Seeing how my students experienced this kind of project was super inspiring for me and taught me a lot. And I'm not suggesting that other teachers are necessarily doing it wrong, by the way. The circumstances of my classroom were much more flexible than most. There were only a handful of students, and also it was a private school, so I kind of got the freedom to make the rules. But in most other cases, when you have a system dominated by standardized curricula and tests that evaluate the student's ability to pattern match all the rules and formulas they memorized to the canonical problem archetypes, I don't blame the teachers for teaching to the test. I just think that as a society, it would do us well to reimagine how we teach mathematics, to give the students opportunities to use their creativity, to discover patterns, to form conjectures, to be wrong, and to pursue mysteries, because they can. And from what I've seen, even though most people have never experienced math this way, they tend to enjoy it a lot more when they do. What I'm trying to do on this channel is show people that math is beautiful, and that there's so much more to it than memorizing a bunch of rules and formulas. Now, the topics I choose to cover generally tend to be more advanced, and probably primarily appeal to people who are already deeply interested in the material. But if you are someone who has self-identified as disliking math, I really hope this video sheds a new light on the subject. Or if you maybe have friends or relatives who are math students and have self-identified as disliking math, I really hope you'll share this video with them. Because a change in perspective, especially from a young age, can be incredibly powerful. I hope you enjoyed this different style of video than usual. I've had these ideas circulating in my head for a while now, but got the inspiration to put them together into a more coherent piece recently. Let me know in the comments what you thought, and if you did like it, consider supporting me on Patreon and joining the names you see on screen now. Thanks so much for watching, and I'll see you next time.